Welcome back. In the last clip, I did not manage to cover all the learning objectives I wanted to. So here, this clip will just keep going. So I want to look at identifying change in direction and changes in speed from position and velocity versus time graph, as well as how to sketch motion graph. And actually, we'll start with the latest one. So I want to start by looking at the position versus time graph and sketching the corresponding velocity versus time graph. This is a skill that is important not only for mechanics, but there will be other parts of physics that will require you to do something similar. And as well in math, when you go and find the link between a function and its derivative or its antiderivative, you will see that it also connects to all that. The first thing to do is to select a few key points and to draw the tangent line at these points. It's no surprise why we're doing this. We know that the slope of the tangent line on the position versus time graph will give us the velocity. So what key points are interesting in here? I would definitely say t is equal to 0, probably here at the bottom at t is equal to 2, at 6 it seems to be the steepest, and then maybe at 9. So with all of these, you just want to draw the tangent line. It doesn't have to be perfect, it's really just to help you think about the problem. So here it's flat, at 6 it becomes positive and quite large. And then we're back with the flat line in here at the top. So let me just readjust these a little bit. Okay, so we have something like this. So the second step is to look for each of these and then just see how it would look in the velocity versus time graph. So for this one, we see that the slope of the tangent line at t is equal to 0 is negative. So we know that the velocity will have to start somewhere on the negative side. I don't know where exactly, but somewhere in here. Then at t is equal to 2 seconds, the slope of the tangent line is 0 because the tangent line is flat, is horizontal. So we know this will have to be 0. Then you see that the slope of the tangent line would be increasing, getting steeper, more positive, until it reaches a max at 6. So I know that at 6 it will now be positive. And then this completes the first part that looks like a parabola. So what I want to do with all of these points is just to make sure that I have something negative at first, something 0 at 2 seconds, and something positive at 6 seconds. But always with the same slope, because if I assume that the acceleration is constant, this means that the slope on my velocity versus time graph should also be constant. So knowing these restrictions, I know that I have to be 0 at 2, so I can draw a straight line that will start, maybe I'll start it a little bit higher actually, and that will go up to 6, like this. Something that will look like that. Negative velocity at first, 0, then positive. And then if I look at what's going on afterwards, at 9, I'm back with the 0 slope. So this means that as I leave the 6 seconds and I go back to 9, it should be looking like this, so that I'm back at 0. And then finally there's a little last stretch in here that should be right on top of the 0 line because the position does not change for this part, so the velocity should be 0. So essentially what I've been doing is just looking for key points, finding the slope of the tangent line, copying it back on the velocity versus time graph, and realizing that because we know we are dealing with constant accelerations, we have a first portion in here of constant acceleration that is positive, and then another part that with a negative constant acceleration, and finally a last part with 0 acceleration. I want you to realize as well that the same strategy that we use in here could be used if you were going from a velocity versus time graph to an acceleration versus time graph, because it's the same idea. If you have a velocity versus time graph, the slope of the tangent line just gives you the acceleration. Let's look at a couple of examples. The first one in here on the left is position versus time, and I want to find velocity versus time, and the other one is a velocity versus time graph, and I want the acceleration as a function of time. So hit pause, try this on your own, and come back afterward so that we can discuss the solution. Okay, so for the one on the left, a key point would definitely be what we have here at the beginning and then maybe at the end. And in the middle, you see that the slope just gets more and more negative. So at first, the slope is nearly 0. So we know that our velocity at the beginning is about 0. and then the slope becomes more of the tangent line becomes more and more negative. So we know that the velocity will be more negative as we go. And finally, because we are expecting, or assuming I should say, that we're dealing with constant acceleration, this means that we just have to start from 0 and then just link these together so that we have negative velocity all along. For the other one, it's a little bit similar. We want to look for the slope at given points, but you see that we have straight lines in here. So at first the slope is constant and positive. So we're expecting to have a line that will be positive and constant. And then the slope will be negative and constant. So we're expecting an acceleration that will be negative and constant. So actually, then you have to connect these. Some textbook will leave it like this. Some textbook will have just a dashed line that is connecting the two. Other textbook will have a full line. It doesn't really matter. Okay, physically anyway, nothing happens instantaneously. So this line is never truly vertical. It's always basically a very steep but not infinite slope, or negatively infinite in here. So that summarizes what happens when we have a function and we want to find the rate of change of that function. The next tool that I want to discuss with you though is what happens when we want to go in the other direction. So what if we have, for instance, a velocity versus time graph and we want to find the position versus time graph? You kind of have to think backward now, and that's a little bit harder, but it's not that bad. Okay, so first thing is you have to set the initial position. This is not given by the velocity versus time graph. So really, if the problem is not specifying anything, just choose the origin or actually whatever point you want. There is no right or wrong answer for that. Then, just as we did before, pick a few key points on your velocity versus time graph. And here I would pick probably the beginning, t is equal to 2 again because the velocity is 0 there. Then at 4, at 6 probably, and then back at 0. That would be my 5 points that I think are key. Then we have to start and think backward. So the value of v on the graph at these key points will give us the slope of the tangent line on the position versus time graph. So at t is equal to 0 second, the velocity is negative, which means that the slope of the tangent line will also be negative. Then when I reach 2 seconds, the velocity is 0. So the slope should be 0, which means that my tangent line will now be a flat line. Then I will reach 4 seconds. At 4 seconds, the slope will be positive now for my tangent line. So I have something that will look, I don't know, maybe like this. And then the slope does not change until I get to 6 seconds. So I'm expecting to have something that will be straight for a little while. Then after 6 seconds, the velocity starts to decrease until it reaches 0. So I know that my slope by 10 seconds will now be flat once again. After that, we have to essentially connect the dots. In the first portion, we know that the velocity has a constant slope, which means that the acceleration is constant. Therefore, on the position versus time graph, we expect to get the parabola. So we want a parabola that will match the different slope that we have here. So let me try to do my best. So we have a parabola that will start downward, hit flat at this point, and then come back to 4. Then from 4 to 6 seconds, my parabola should be straight. So I would just want to extend it in a straight line until I reach 6 seconds. And after 6 seconds, it starts to get a slope that will be less and less positive, so that will reach 0 eventually. So afterwards, I want to curl down until I reach 0. So you see that I'm not matching my lines perfectly in here. It doesn't matter. They're there just to guide us to be able to draw the correct shape for the position versus time graph. So to summarize, it's similar to what we did before. The extra step is that at the beginning you have to choose where you start, or if it's given in the problem, just start from that position. Then choose a couple of key points, and then it's thinking backward. The value on your velocity graph gives you the slope of the tangent line on your position graph. So you have to go and just connect the dot afterwards using straight lines or parabola. And just as we saw before, the same strategy can be used if you're going from an acceleration versus time graph to a velocity versus time graph, because it's the same kind of idea. The acceleration being the rate of change of velocity, we have the same connection as in here. So let's look at a couple of examples. So same as before, so please hit pause, try to find the solution on your own and then come back. We have two problems in here. First one going from v to x, so velocity to position, and the second one acceleration to velocity. So in the question it says to start from the origin, so we get the first point to be just in here, and at first the velocity is positive, so we expect the slope to be positive. In the middle the velocity is 0, so we would expect a slope to be 0, the tangent line, and then finally the slope of the tangent line should become negative. Because of the symmetry that we observe, we know that we are dealing with a parabola that will look the same on both sides. So I'll do my best in here. You start going up, flat in the middle, and then it curls down until you get there. And that's it. We have our position versus time graph. For the second example, I'll start with the velocity of 0. And you see that the acceleration at first is positive and constant, which means that my velocity will have a constant slope. So we know that we will start with something like this. Then for the next portion, the acceleration is 0, which means that the velocity does not change. The slope is 0. And then afterwards, you see that the acceleration becomes negative. So we know that the slope of the velocity curve should become negative as well. And then finally, the last part, velocity is just 0. Here I had it go back to 0 because the area under the curve of these two parts of the curve look to be pretty much identical. So in some sense, it will remove from the velocity what was added in the first portion. Finally, I want to go back to the graph we discussed before to discuss two things that are related to qualitative analysis of these graphs. First one is to be able to identify when there's a change in direction. So on the position versus time graph, the change in direction is occurring whenever the curve is actually changing direction. So in here you see at 2 seconds, the object was moving towards the negative direction, and then after 2 seconds, it's moving towards the positive direction. So that one is easy. Whenever you have a change in direction on a position versus time graph, the object is actually changing direction. On the velocity graph though, you see that 2 seconds is when the velocity goes from being negative to becoming positive. So change in direction on velocity versus time graph will occur when you have a change of sign in the velocity. The other aspect that we often discuss is speeding up and slowing down. So I'll do the case of speeding up, slowing down is just the opposite. In here, speeding up just means that the curve gets steeper. Okay, because when we talk about speeding up, the direction is not important, so we don't care about the sign. So whenever the slope gets steeper, it will be speeding up. So in this example, it would be speeding up between 2 seconds and 4 seconds, because after 4 seconds, the slope becomes constant. So to look for it, you want to have the magnitude of the slope of the tangent line to be increasing. And if you look at the velocity versus time graph, well, the same portion, you see that what happens between 2 and 4 seconds is that the velocity is going away from the 0 line. So on the velocity versus time graph, what we're looking for is just that the curve moves away from the horizontal axis. If you want to practice your graph sketching, there are 2 simulations on GeoGebra made by Tom Walsh that are pretty great. So I'll show these around very quickly. So the first one in here is position, velocity, and acceleration versus time graph. What it does is that you can control the velocity versus time graph like this. So you can choose whatever you want, and you can choose also your initial position. But what you can do to use it to practice is just unclick these so that they are not shown. Choose your velocity versus time graph that you want to practice, so maybe something like this. And after you've done it, try to draw your position, your acceleration graph, and then show it again. The other simulation is doing the same thing, but with controlling the acceleration instead of the velocity. All right, hope you enjoyed.